Renewable energy is great, but it cannot load follow. In other words, it cannot provide a continuous supply of electricity to the grid that matches demand. As such, where no hydroelectric or nuclear energy is available, fossil fuels often fill the gaps between the high points of renewable energy production to make sure there's always ample electricity. And this has been going on for years, whilst exit scammers sell you phony energy storage plans which never leave the CGI on some fake science communicator's YouTube video. That means so long as nuclear energy isn't rolled out, the fossil fuel companies will continue to rake in huge profits and pollute the atmosphere, whilst leaving thousands of acres of land totally destroyed by coal mining operations. The fossil fuel companies protect their cash cow by funding anti-nuclear groups and idiots masquerading as academics who will then lie through their teeth in order to keep the general public afraid or at least skeptical of nuclear energy. In 2011, the Fukushima Daiichi power station suffered a loss of coolant accident after a tsunami knocked out its backup generators, which normally provide power to the cooling systems when the reactors are shut down and electricity cannot be drawn off the grid. The generator rooms were supposed to be watertight, but TEPCO were incompetent, and as a result, a person lost their life. Yes, you may not know, the radiation from Fukushima only killed one person, which compared to the consequences of the tsunami and poor air quality is a rather interesting statistic. But it's still a human being who could have been with us today if it wasn't for TEPCO's stupidity. But I digress. As the reactors overheated, the zirconium cladding of the fuel rods began to fail, leaking radioactive fission products into the core. Worse still, at high temperatures, water reacts with zirconium to produce hydrogen gas, and should it come into contact with oxygen, it will explode. To prevent this, nitrogen gas was injected into the reactor, the presence of which will displace oxygen and prevent a hydrogen air explosion. However, as the heat increased the pressure inside the reactor, it was necessary to alleviate this by venting the trapped gases and fission products into a wet well suppression system. The water in this system was able to filter out much of the radioactive fission products, but the lack of cooling due to the failed diesel generators meant that the pressure finally had to be released by venting the gas into the atmosphere, some of which leaked into the outer parts of the reactor building and caused the explosions we all saw on the news that fateful day. Contaminated water in and around the power station was collected and stored in large tanks. The water contained several radioactive fission products such as Caesium-137, Strontium-90, Iodine-131 and Hydrogen-3, aka Tritium, which we will talk about later in the video. The first and most important thing you need to know is that the radioactivity of an isotope is inversely proportional to the half-life. If I have 2 grams of radioactive material with a half-life of 100 days, then after 100 days has passed, I would have 1 gram left. Half of the material has radioactively decayed into stable elements, and in doing so has released a large amount of radiation over a short period of time, making it a hazard. But if I had another 2 grams of radioactive material with a half-life of 1 billion years, then barely any of the material will undergo decay in the same 100-day time span, making it practically harmless. There are other things to factor in, such as the decay energy, the type of radiation, chemical mobility and bioaccumulation, but essentially you can see that the shorter the half-life, the more radioactive an isotope is, and therefore the more likely it is to be dangerous. On the flip side, such elements are not a long-term problem, because they decay away relatively quickly. However, something in between these 2 time spans, such as Caesium-137, has a short enough half-life to be very radioactive, but still a long-term problem. But by far the most dangerous of these fission products is Iodine-131. Since it has an 8-day half-life, making it highly radioactive, it is also mobile, forming chemicals and potentially making its way into food, and it can bioaccumulate in the thyroid. Because of these properties, if Iodine-131 is leaked into the environment, one of the immediate courses of action is to destroy all the locally produced dairy products and avoid their consumption for the next 2 to 3 months. Strontium-90 has a half-life of 28.78 years. It isn't chemically mobile. If you don't eat the dirt where it settled, it won't harm you. However, due to its proximity to calcium on the periodic table, strontium, if ingested, would accumulate in the bone marrow and stay there, increasing your risks of getting a blood cancer. Caesium-137 has a half-life of 30 years, and whilst it doesn't bioaccumulate, it is chemically mobile, able to form water-soluble chemicals. Rather nasty stuff, but there are small amounts of these elements found in the environment already, but they are harmless due to how diluted they are. For example, mushrooms growing close to the Chernobyl power station accumulate caesium, and these mushrooms are a part of local people's diet. As a result, they are exposed to 0.12 millisieverts of radiation per year. For context, your chances of developing cancer begin to increase at doses above 100 millisieverts per year. That is 833 times greater. The ingested caesium won't stay in your body either, half of it is expelled every 90 days. So what can we learn from all this? Small amounts of radiation won't hurt you. Nevertheless, it is a bad idea to dump fission products from the Fukushima accident into the sea, which is why TEPCO set up a system to treat water before releasing it. First, the water is pumped through 2 filtration systems which remove the caesium and strontium. Then the water is desalinated. Then it's pumped to the advanced liquid processing system where other radioactive elements of concern can be removed. From here, the water's radioactivity is assessed. If the water is satisfactory, it awaits discharge into the sea. If it is unsatisfactory, it is retreated until it passes. After this process, is the water completely free of radioactive elements? No. The water will still contain tritium. It isn't really a danger, but thanks to Greenpeace and their cronies, many people are unnecessarily afraid of the treated water being released into the sea. So what is tritium? Well, simply, it is a hydrogen atom with 2 neutrons instead of 1 or 0. It has a half-life of 12 years. The extra neutron makes a tritium atom unstable, so at some point after 10 half-lives have passed, the extra neutron will convert to a proton and an electron. The hydrogen atom thus becomes a helium atom, whilst the electron is ejected from the atom at high speed. These high-speed electrons are beta particles, a type of radiation. How dangerous is it? Not very, and you can see my other videos for a more detailed explanation of why. Now, these beta particles don't travel very far when released, and they don't carry much decay energy. That's not to say that a large amount of tritium isn't harmful. It is. But it would take considerably more tritium than what is present in the treated Fukushima water in order to cause harm. It's the same reason that potassium-40 in bananas is practically harmless. It has higher decay energy than iodine and caesium, but the half-life is thousands of times longer, so thousands of times less radiation is emitted. And this is the kind of understanding of radiation that fake environmentalists and fossil fuel companies don't want you to understand. Radiation is a fact of life. In the upper atmosphere, you'll find krypton gas and cosmic rays. Coming out of the ground, you'll find radon gas, and in the sea, you will find uranium-238, potassium-40, and tritium. But to show you why the titrated water from Fukushima is harmless, let's do some math. Yay, math. Between 0 and 500 meters, the total amount of tritium in global oceans is around 26.8 kilograms. Industry adds 78 grams per year, and naturally forming tritium is 258 grams per year. Switching to becquerels, another measurement of radiation, Fukushima will dilute and release the titrated water at levels equivalent to less than 1,500 becquerels per litre of water. That is approximately 1/7 of the World Health Organization's drinking water quality guidelines. But how much tritium is that? Well, we know that 1 terabecquerel, aka 1 trillion becquerels, is equivalent to roughly 2.8 milligrams of tritium. We can calculate 1,500 becquerels as being 1.5 times 10 to the -7th power percent of 1 terabecquerel of tritium. The same percentage of 2.8 milligrams is 4.2 times 10 to the -9th power milligrams of tritium per litre of water. If the plant discharged 500,000 litres of water per day, that is 0.0021 milligrams of tritium per day. Times that by the 365 days of a year and it's 0.665 convert to grams, and we have a grand total of 0.0007665 grams of tritium per year. Remember, natural input of tritium in the sea is 258 grams per year, meaning the annual input of Fukushima's treated water is 333,985.65 times less than that of naturally produced tritium per year. Not so scary when you have the numbers in context, is it? Fukushima is quite literally pissing in the ocean, but that hasn't stopped fear-mongering liars from trying to keep you afraid. China, for example, issued a ban on Japanese seafood, whilst their own nuclear power plants on the coast regularly contribute to artificial input of tritium into the sea. As you can see from this video, the worst case scenario for a nuclear accident in modern light water reactors is both highly unlikely to happen when safety measures are properly adhered to, minimally dangerous to public health, and after a proper cleanup operation, inconsequential to the local flora, fauna, and marine ecology. Thank you for watching. If you enjoyed this video, why not leave a like and a comment? If you wish to further support my channel, feel free to subscribe or donate via link in the description. Thanks again.